Okay, now let's talk about some important concepts in the operating system. Kernel. So we have the operating system has two mode, kernel mode and user mode. We always working at the user mode, but never working on the kernel mode. It's because kernel mode is a major part of the OS. It's a part that is stay in the main memory and control the execution of all other programs. Its kernel mode is control all other programs, and other programs must use the system call to from a user mode to the kernel mode. Use system call. You cannot directly access the kernel mode. Kernel mode is a part of operating system. I know it's very abstractive here, but we have a lab. I will discuss later. We have the lab to let you programming on the kernel mode, and we now later I will show example. The kernel mode. Kernel mode will all of our programmings written in a high level language C++ on the user mode. It uses a system call to access the kernel mode. Okay, kernel mode. A system program. Okay. A system. Oh, not this pen, not the pen. Laser point. A system program. Is not part of kernel mode. System program or application program is also not part of operating system. The kernel mode is very special. Today, operating system, general purpose, and mobile phone also include the middleware between the user and the kernel. It has the middleware. So the operating system is layer by layers, user, kernel, and middle layers, such as the it's a software framework, database, multimedia, graphics, it to show the UIs. So this figure, I like this figure. So it has a user mode and the kernel mode. Sometimes we call the user space of the kernel space. It says the user space has a user application, and the glibc is a library. User application glibc is all in the user mode. We always see that and when programming. But in the kernel mode, we have the system call to access the kernel of the operating system. And the kernel will access the hardware. The kernel will manage all of the process, all of the manage the memory, all of the resolve of the hardwares. And you only can use the system call to access the kernel. So this is totally separate. This is to protect the operating system, protect the kernel. Otherwise, any application here, like Facebook, Twitter, can directly access the kernel. That's very dangerous to destroy the whole operating system. Okay, this is the kernel. In this course we use Linux. Why we use Linux? Because Linux is open source. We just say the kernel. But what is kernel? Can I touch it? Yes. You can download from this. It's a totally open source. You can use the manual. You can compile and run it. But this is only the kernel. You see, the kernel don't include any applications. So it's hard to make your kernel run. You can try on a virtual machine. Now compile the kernel and make it run. When I was a software engineer, we always use this Linux kernel for embedded system. We can cut some useless things like some command line we never use it. Some for some of Wi-Fi, some of the use it. We can cut this. Like it's pruning the kernel, makes the kernel very small. It can run on operating system. If you have time, play with this. Linux kernel is totally free. Don't think about the Windows and iOS. It's closed source. It's not open source. You cannot download. Okay. Because this is only an introduction part. We briefly discuss every part. Details will see later. So this is the computer system organizations. This is memory. It's our computer memory. This memory uses a system bus. System bus to connect all the things like CPU. CPU will connect with the memory with system bus. And all the other devices like this, mouse and keyboard, important, mouse and keyboard, printer, a monitor. Yeah, this is also important. Printer. We use this to connect it to the memories. So when you try to operate all of this device, it's all within the memory because all this is mapping to the memory address. The memory address is operating just like intermediate layers. You use access and memory address to access it. Okay, I/O structures. A general purpose computer system consists of CPU and multiple device controller that connects through a common bus. Like I said, it's a common bus. And we have a device controller. We have the bus. We must have a device controller to control that. Like this, the monitor and the graphic adapter access the monitor and connect to the memory. How can we control that? We need a device controller. That is typically called a device driver. We have the hardware, we have operating system, and the manufacturer must provide a driver to that. But good thing is currently the driver is automatically installed on our computer. But when I was young, I must install the driver by myself. Like a driver. Okay, we talk about lots of let's see some code. What is the kernel? What is driver? This driver is always in the kernel mode. Driver, because driver is not an application. It's an adapter for hardware. So it's must in the kernel mode, not in the application mode. Because it's for example, this is a minimal USB driver. As an example, this is the code. This programming is totally different with the application programming. It's because we want this module you need. We need this module as a USB simple. We need this module, and then you need this module and exist module. This is to this init will execute when we insert this module to the kernel. So when we compile this code, we will insert this module to the kernel. This kernel file is always has the extension name of KO. Kernel mode KO. This is kernel mode, and we insert it to the kernel mode. And we also can remove it from the kernel mode. So when you insert it run this function, and then remove it run this function. So all of this is executed in the kernel mode because this is the USB driver. This is find minimal ones. So you see, this includes the header file of Linux kernel. This is the kernel environment programming, and it doesn't have the printf. It has the printk. It's important debugging that can print information like printf. No printk, it has the printf, and it's say the init USB simple init. USB simple init is just register this device to the bus to the operating system. So here init, this is hardware related, right? If you don't understand that, that's fine. As I just tell you, this is a totally different environment of a kernel programming. Kernel programming is different. Okay, and it's running in kernel. Because the USB drivers, everybody has a USB plug into the computer. It will call this a USB driver. It uses a USB driver. It's not an application. It's used by all of the USB device. And the application is one of the application that may read or write files to the USB. Okay, good. And I/O device and the CPU can execute concurrently because I/O device is like a CPU, like the USB is very slow, and the CPU is very fast, right? Some very fast. They can run concurrently. Each device control in charge of a particular device type and has a local buffer. Local buffer is means to solve this difference of the speed, different speed. And each driver has a device driver. Matter we saw the minimal USB driver. Each device must have the driver to manage it. And I/O is from the CPU moves data from the main memory to local buffers, and the I/O is from device to local buffers. So it's moving data. Device controller inform CPU that has finished the operation by causing interrupt. Interrupt is a very important concept. Interrupt. When I plug in this USB device to my computer, how the CPU know that? How the CPU know that? It's two ways. One is busy checking. I always ask you, are you there? USB, are you there? This is the busy checking. I always ask you, are you there? But it's not efficient, right? It's not efficient. So interrupt is will come. I'm busy doing my things. You notify me that you come. Oh, USB, you come. I should read the file from you, read the write file from you. This is the interrupt. So device controller informs CPU that has finished its operation by causing an interrupt. This is a very important concept in operating system. Interrupt. And the interrupt transfer control to the interrupt device use the interrupt vector. That's the implemented details of in the operating system. I just talked about is hardware interrupt, like a printer, USB as a hardware interrupt, and the software interrupt like a trap and the exceptions in software generated interrupt causing either by error or by some request. For example, your application, okay, Facebook run on your cell phone, don't have enough memory. The Facebook will cause interrupt of a trap. No, it causes a trap. I don't have enough memory. I want more memory from an operating system. Yeah, the operating system will allow you more memory for this application. That's a trap. The operating system will not busy checking. Busy checking is not efficient. Will not be always asking. And because the CPU is very busy. CPU is very to do a lot of things. CPU don't have time to always ask you. That's the waste of resource. The operating system is interrupt. All the operating system is to dealing with this interrupt. Okay, that's a diagram. This is the CPU. The CPU is the user program. User program is an I/O interrupt process. And this is your application. For example, this is your Facebook. And when it comes to here, it's called the interrupt. Want to read data from the file. Want to read data from a file. It's called the I/O. It's an interrupt signals and transaction or using interrupt. I want to read files from from your SSD, from the SSD. So currently the CPU will be idle. Yeah, CPU is very fast. It's waiting that I need the file. Give me the file. CPU will idle and you will waiting, but later CPU will continue to do the work. This is still has I/O interrupt. I/O is very slow. CPU is fast. The speed not match. This is so the I/O. So I/O, this is the I/O request. Read files. There's a transferring. Transferring, and this is transferring data. This so the CPU will never have time to ask the disk. Okay, do you have some file to send to me? No, it's caused by the interrupt. So the concept of interrupt. It's not use the busy checking. Not use busy checking. Okay. Okay, the important concepts are here. Clear here? Because this is instruction part, we will discuss these details later. Interrupt handling. So operating system preserve the state of the CPU by storing the registers and the programming contents, and determine which type of interrupt is the account. We have lots of interrupt, which is the account, and separate segments of the code determine which action should be taken for each type of interrupt. So the CPU has a vector, and each vector has an index, a number, and the action which the interrupt will cost. So this is the implementation details. Okay. Let's say some easy topic. Have you seen this? Yeah. Wilson. This port is disappeared now, right? Who can tell me what is for? What is for? Yeah.
For the desktops, the old desktops.
Old desktop, the connector.
The mouse and the
Good. It's only for old desktop. Why? Because this is interrupt. This is the keyboard and desktop using interrupt for input. I guess the interrupt is a keyboard will send a signal to the CPU that, oh, I have input. The CPU will stop its work to dealing with the input. So this interrupt will be efficient, right? Efficient and save the resource. CPU don't need to spend time to always checking. This is for older machine, but this is for current machine. Current mouse and keyboard connected with the USB, and this is use Poly. Poly is video chat. But why modern computer use do not use interrupt, use Poly video chat? You know why? We talk lots about interrupt. We have lots about good things about the interrupt, but not discuss the advantage of Poly. This is the advantage of Poly video checking. So the mouse and keyboard will always ask the CPU. Okay, once I have I always tell the CPU all my move. Why modern CPU has this? Someone can talk? Okay, let's okay, good. This is because our modern CPU is really powerful. Our CPU is really fast. How many cores of your CPU has? How many cores? 2 cores. How many cores of your CPU has? Your laptop, 2 cores. Sorry, you only have 2 cores. No, it's 4 cores. Yeah, 4 cores. So 4 cores. Our CPU is really powerful. Why we not use 1 core to dealing with the keyboard and mouse input? Because we want a low latency, really fast response. Like your programming play the game, CS2, right? It need a fast response and low latency. This is the best. This is the best. Because keyboard and mouse, this is the best. Like my mouse here, it is connected with Bluetooth, and my old one, first generation of this mouse has a high latency. It's very slow. I'm not comfortable to use. And this one is good, has low latency. So user experience is more important. And our CPU resource is high, 4 cores, and CPU can take 1 core to dealing with the request. All the machines is possible. All the machines only has 1 core. So busy. Right? Clear here. Clear here. The Poly and the interrupt. But how about the printer? Printer use the interrupt or Poly. Printer. Fine. Doesn't matter. I always ask you questions. It's just to try to answer. It doesn't matter right or wrong. Just let you do your work. Right?
Wouldn't it be interrupt for printer?
Why?
Because printers would be idle. It wouldn't be working unless it is prompted
Yes, good. Printer is always idle. How many times you use the printer? 10 times a day is too much, right? So why the CPU will always ask the printer, okay, do you have something to print? It's not like that. And the latency for printer is kind of better. Okay, if the printer slow 1 second, I do mind. You don't mind. Yeah, printer. You don't mind. So printer is a better user interrupt. Keyboard, mouse, and the monitor. Low latency monitor is must use porting. Okay. Computer startup. Computer startup is we have the booster trap program. It's loaded at the power of a reboot. It automatically load a booster trap program. It's for before loading the operating system. Booster trap is tell the operating system the OS in where? Where is the OS? In which disk? Which location? And typically it's stored in the ROM. ROM is not stored on the disk because the disk is always managed by the OS. It's stored in the ROM or EPROM, generally known as a firmware. Firmware to let the operating system know, to let the machine know where is the operating system. Firmware. It initialize all the aspects of the system. Loading operating system kernel and start the example. Then it's operating system can load in the kernel and start the system. Okay. Okay. I use a Mac, so I always take my Mac as an example. The Linux, the Windows has the same things. This is a startup in the Mac. It's let me choose which disk I use the startup. This is not part of operating system. It's a bootstrap program. Okay, good. Okay, this is used in the Windows machine, desktop. It let you choose what's your first boot device? What's your second boot device? We'll try to install the Windows, right? You must choose the USB as the first device. So the system will the bootstrap will loading the system from USB, not from a local disk. So set the first boot device as USB. So you'll try to install the operating system. Any questions? No? Let's go on. Storage structure. CPU can access only main memory. So CPU access only the main memory. What's the main memory? I suppose you know that. Who can tell me how big your main memory? How big of your main memory in your desk or laptop? How big is it? You know, main memory. Yeah, you know, 16 gigabytes. How about yours? You do not. Yes. Maybe 16. Currently, the volume machine is 16. Yours? 32. 32. Good. Little expensive. Okay. Currently, the main memory is 16 or 32 gigabytes. It's a program must load into the main memory ROM. They must be stored in all the program must be stored in the main memory, right? And the main memory is volatile. Volatile means when you power all of the things in the main memory will stay or gone. Will gone. The main memory cannot stay data without power. That's why you need secondary storage. Secondary storage like disk, SSD. How large of your SSD?
1,000.
1,000. 1,000 gigabytes or 1 TB. How about yours? 128.
128 gig.
Oh, what is it? You have the device is MacBook.
Yeah.
MacBook is very low. 128 for 256 gigabytes. Mine is 256 gigabytes. The Mac is you must pay more money to get more storage. This is the Mac world. But all the Windows machine always has 1 TB or 2 TB. This is a disk. When the power off, all the data still in the disk, right? If it's all form of the memories provide a ring of bytes, a ring of bytes, and each byte has its own address. So you can virtually say all of the storage is a ring. As physically it's stored in different format. You can you can see it's all a ring, and each byte has its own address. Okay, this is important. Storage device hierarchies. As I said, the storage has a different speed. The USB, okay, laser point. Okay, CPU has a register and a cache. CPU has a register and a cache, and the cache will connect to the main memory. Main memory will connect to the non-volatile SSD, and the SSD connect to the hard disk drive. And no desktop don't have this. So laptop don't have the hard disk drive. Because hard disk drive is more cheap. It's cheaper and has a lot of storage. Cheaper than SSD. SSD is much faster. SSD is much faster. This is faster. This is faster. It's slower. SSD is more faster, but more expensive. Whose laptop has a hard disk? Whose laptop has a hard disk? No, I guess no. Yeah, you have a hard disk.
In my home.
My home is a desktop, right? In your desktop, you always use the SSD store the operating system. Faster start, and the data stored in the hard disk. And then as SD card, USB drive is much more slower. The last one is the magnetic tabs. Magnetic tabs. This is have you seen this before? Magnetic tabs. No, it's too slow. I think it's already out of date today. Say the fast storage is always smaller. The slow storage always fast. They have a different speed. The speed is not a match. That's why they have a different layers. So important thing, the CPU including register and the cache. Also because the CPU is really fast, but the main memory is very slow. So that's why we need the cache. We can load the part of data from main memory to the cache, for the faster accessing of faster accessing of CPUs. Okay, now you know we need a cache, right? And do you know how much cache you have in your CPU? You know? You don't know? Normally we have a CPU have 3 levels of cache because the cache is often have a similar architecture, different cache at different speed. The cache, largest cache is largest cache is very slow, and the smallest cache is very fast. 3 levels of cache. When you buy some computer, okay, you must ask, how large of my cache? Do I have some cache? Oh, it will be discussed in the later. Okay. Storage definitions. We use storage. I think you already know that. KB, kilobytes, KB, and the megabytes is megabytes MB, gigabytes GB, petabytes TB. Now our disk is much larger than TB, petabytes. Any questions here? I suppose you know this, okay? So we always because we are in computer science, we always discuss byte How many bytes? One byte is 8-bit, right? One byte is 8-bit. Okay, this is important. This is the speed of different types of storage. Which is register. See, this is a register, and size is always less than 1 KB register, and the time is really fast, and the bandwidth is really large, and managed by the compiler. And applications cannot manage this. The compiler can optimize. Okay, we can use a register to fast for the efficiency. And second is the cache. The cache is always like 16 megabytes or 32 megabytes. Some good CPU has 32 megabytes cache. The cache size is compared with register is really large. Okay. Who can figure out how much cache of your CPU has? No? Check that. It must be in this 16 or 32. If your CPU is very cheap, it only have 2 megabytes of cache. Main memory, normally less than 64 gigabytes. Main memory. And so the accessing time is slower, right? Slower, and the bandwidth is narrow. And the solid disk SSD less than 1 TB. The accessing time is always much slower. But the last one is magnetic disk. It's always 1 TB, 2 TB, or 10 TB, but it's slowest. Okay, remember, this is important. We have lots of technology because the different speed is not matched. Okay, one question. Now our computer is more and more powerful. And for example, the main memory is really large, up to 1 TB if you have enough money. You can configure a computer has 1 TB memory. So our memory is large enough. Can we replace a solid state disk? We don't use the disk. Our main memory is large enough. Can we don't use the disk? Yes or no?
No,
No, why?
because main memory is so volatile, you lose your operations.
Yes, good. Main memory without the power it lost data. It must store into the solid disk. Right. And the other question is with the development of technology, if your main memory is larger, and cache can become larger, register is larger, more efficient. But our CPU have lots of things to do, like our AI, artificial intelligence. Okay, for example, now my Mac has Apple Intelligence. So and the old CPU cannot support this. Yeah, cannot support this. Well, CPU is more powerful. It will have a more powerful application. Use all of the hardware resource. That is why your computer becomes slow and slow. It's not CPU's problem. It's because of our application, our app has it's become bigger and bigger. New features. It try to use all of the resource of the CPU. Okay, let's go on. Okay. Oh, I just talk about that we have this 3 level of cache. Okay. This is my desktop CPU. You see, it has 3 level of cache. L3 cache is 36 megabytes. 36 megabytes. And the L2 has 32 megabytes. The L1 cache has 2.1 megabytes. This is the Intel Core i9 CPUs, and this is the most expensive ones. Kind of like item. And all the other is much cheaper. Cheaper ones is it's cut the cache. Okay, why it has a 3 level of cache? Why it has 3 level of cache? This has a thread, it can support 32 thread. 32 thread, it's a 24 thread, 16 thread, 12 thread. That's why it's the most expensive. Okay, my question is here. Why it needs 3 level of cache? Can we use the one level cache? Yeah, try.
But wouldn't it be because it's multi-threading as well? With the processor?
No. I guess that. Okay.
Because each cache is faster.
Yeah, the speed is not match. L1 cache and it has a register. Register is the most the fastest ones. But L1 cache is try to match the speed of register. L2 cache is slower, but try to match the L1 cache. L3 cache is slowest, match the speed of L2 cache. Speed is different. Speed is different speed. That's why you need 3 level of cache. It's a very common strategy to dealing with a different speed. Okay, different speed. You know, if different speed, L3 cache is much slower, so the CPU will fetch the data from the cache. It's very fast and don't need to fetch the data from the memory. Memory is slower. Fetching data from memory, CPU must wait. Why CPU must wait? Why CPU must wait? So CPU can do other things. Or CPU can directly fetch data from cache. Right? Okay. Or the migration from data A from disk to registers. So when a program is run, it starting from magnetic disk. Load the application from the disk to the from a disk to the main memory. Okay, from a main memory load to the cache. We have a 3 level of cache. Remember, 3 level of cache. And from level 3, level 2 to level 1, and then load to the hardware register. So the program can run. And multiple multiprocessor environment, because currently lots of CPU have 4 cores. Multiprocessor environments must provide cache coherence. Cache coherence in hardware such as CPUs have the most recent value in that cache. Coherence means we have a different cores. The data must be consistent with each other. One core modifies the data, it must notify other cores. So this one core, I modify the data, but other core don't know. It's error. So that's why with the current CPU, multiprocessor must cache coherence. This is not a part of the operating system. This is like a CPU design. When you design CPU, you must ensure this cache coherence. The value is always correct in the cache. Okay, I saw a simple example of a cache. So the CPU will read the data from the memory, right? So CPU not directly read data from, for example, CPU will read a 1. CPU will read 1. It's from a cache. It's from first time it will read from a memory, and next time it will load into the cache, and next time the CPU will directly read data from the cache. Don't need to load it from a memory. But if the data is not in the cache, the CPU will directly go to the memory to accessing it. So that's why it's important that how can we, this is missing. So if the CPU cannot feed the data into the cache, that's the missing. If the CPU feed the data into the cache, that's the hit. CPU hit the data into the cache, and CPU avoid to access the memory. And a CPU missing the data, the CPU must access the memory. My memory is slow. See our lab, our second lab. Our second lab is for this cache. How can I write a cache-friendly program? Cache-friendly program. So let the CPU always read data from the cache, not from the main memory. main memory, it will become faster. This is hardware related, right? Because the CPU has this design, cache-friendly program will run much faster than the not cache-friendly programs. Good. Operating system structure operating system provide the environment with a switch program that exaggerate. It's a multi-programming. It's a multi-programming. So organized jobs. The CPU always has thousands of jobs to execute. That's why we need a job scheduler. And some of jobs must wait because we only have how many cores in your desktop or laptop? You have 10 cores, but you have thousands of jobs. Like I use this. This is my active monitor. So I have thousands of processes, thousands of jobs, but only have like you have 10 CPUs. It's not enough. So some of the application or program must wait. Like there's a PowerPoint or Outlook. That's my favorite using. Google Chrome. Some of program must wait. And that's why we need a job scheduler. Job scheduler to scheduling all of them. And even we have multiple cores. I guess the 32 cores is the most one. We have thousands or 10,000s of jobs. So we must need a scheduler. Okay. Memory layout. So the memory will loading from the memory will separate for different process. This is for process 4, process 3, process 2, process 1. And max here in this part is for the operating system. And it will process has its own memory address. And each of the memory address will never affect others. So from for your programming experience. In this application, can this application access other applications memory? No? So my PowerPoint can access the Facebook's data. Both are application. My PowerPoint can access my Chrome browser data. No, it will leak in the privacy and it's not safe. So this program, the memory space will fit into this part, and process 4 will never access the memory of process 3. It's protected. Each of the process will be independent with each other. The memory space. This is a good design, right? But old operating systems like MS-DOS, like the very old ones, they don't have this mechanism because at that time the computer is very expensive and only has 1 or 2 functions. Yeah. But now operating system must separate all of the process. This is what we'll discuss in our memory management. Our operating system develop the whole technique to implement this. Each of process has its own memory space. So, for example, in this point, I can never access the memory of other application. Yeah, I don't know. So the point will never access others application. If the point will crash, so have some bugs, all the other applications still runs very well. I just need to quit this application. Okay, we hope I can finish this. Time sharing, multitasking. As I said, we have thousands of application, but we only have 10 cores of CPU. 30 cores, 32 cores is very expensive for CPUs. So how can we schedule that? One method is we can time sharing for multitasking. So each of the application has a time slice. CPU will switch jobs for each of the time slice, and that can indicate for each of them running time slice. So this application point running in a time slice. When the time's up, it's moved to the next application, my Facebook, my Outlook. Each process has its time slice, and each core, each user has at least one program exactly in the memory. Exactly the memory. It's old. I should update it. So each core can run a process, right? Each core, 32 cores can have 32 processes run in parallel together. That's why multi-core CPU is more powerful. It can physically run in parallel, right? And this is the kind of time sharing scheduling. And when you use the computer, maybe you never realize that because from your feeling, you feel that all of the application running at the same time. This is a fake. Okay, can you understand? This is a fake because it switched too fast. So from your side, you see, this is running at the same time. Actually, it's not. It has a time slice, different time slice. It's running sequential for each core. I have 16 cores or 8 cores, I guess. 8 cores. So 8 processes can run in parallel. And if different time slice. I get it? So the operating system is important for different time slice. Okay. All modern system has a dual model operating system. It has as we discussed, has a user model and kernel model. And as a mode bit is provided by the hardware, it's indeed supported by the hardware. Some instructions are designed for privilege only executed in the kernel mode. So this is the CPU also supported. So CPU has some instructions that can only run in the kernel mode, not in the user mode. It's very dangerous let you to use this in the user mode because this application may destroy other applications. It's dangerous. So that's why the CPU has a privilege. Or the transitions from the user mode to the kernel mode. And this is separate from this two mode. And it must use the system call. User process exactly must use the system call. It calls the trap. As I said, trap is the interrupt. The kernel mode will never like busy checking, asking the user processing, you have something let me to do? No, it calls a trap. Trap is a software interrupt. Trap, it calls an examiner in the system call. And when the return to the user mode, it's separate, only in the system call. Timer. Also, timer is a hardware supported that's used inside. Always need a timer. Like, do you remember a time slice for scheduling? So you need a timer. Its timer is also supported by the hardware. It's okay. Key functions of operating system, and this is main topics we covered in this class. Process management. Can we say that thousands of processes? We only have 16 cores. We must manage them, allocate resource, process management, and memory management. We only have 16 gigabytes memory, but thousands of applications. How can we manage this memory? It's not enough. But how can we manage this? Storage and file management. It's impossible for us to directly access the disk. So it's important. It's a hardware. So the operating system manages the storage and file system, and you from a user's view, you see this is vector. All of storage is vector. And yeah, you don't need to worry about the details. Right? And last thing is the protection and security. MacBook is a very proud of his security. So that's lots of people buy Mac. Security. Protection, security. Okay. And On the process management, okay, for example, process management is a programming executive. The program is a passive entity, and the process is the active entity. Program is on the disk. It's not running, it's passive. When it is running, it must be loading from the where? From a disk to the main memory and to the CPU registers that become active. Memory management, it need to allocate and delocate the space. Allocate and delocate the memory for different process. File system. How can you create, delete files? Manipulate the file, the copy, and mapping files to secondary storage, backup files, or the file operations. That is file system management. Last thing is have you seen this old ones? This is from a textbook. It's a very old PC motherboard. This is for CPU, right? This is the processor socket, and this is the DRAM slot. So all this, and this is the PCI bus slot. And here you can install your video card. All of them is communicated with the CPU bus. Okay, this is the modern one. This is the modern motherboard. Looks much better. It's much beautiful than before, but the structure is totally the same. So all of this I/O device or the memory will connect with the CPUs. Right? Okay, I think this last ones. Okay, in this class we gave you a very brief introduction of the operating system. And next class we'll discuss the details. That's for the next class. And next hour is my office hour. I will be in the office. Any questions are welcome.
There is lab start today.
Yes, we have that day. Where's lab? Don't forget our lab.
So I saw all those slides in last week.
Yeah.
But I see the some that.
Yeah, I know.
You want to-
It feels pretty.
I looked at this behind before, but I don't know if I'm covered anything.
No.
So, there's a lot of different difference. Even so.
With my
Is there any way that we just not hold our lecture?
I already.
Use it or not? When you send them.
I can send you this one. Just sending that.
So it won't be on any of the mountains here, like.
No, I can't do it in person. I tell you nothing, and also I think kind of. No, my work. I try to encourage students to come.